Well, good evening, everyone. My name is George Iwama. I have the great pleasure of serving the Faculty of Science as their Dean. I'd like to thank every one of you for coming out this evening to the 19th Herzberg Lecture. The annual Gerhard Herzberg Lecture is part of a long-standing series of public lectures of distinguished speakers in honor of Dr. Gerhard Herzberg, one of Canada, one of the world's most distinguished scientists of the last century. The lecture is sponsored by the Faculty of Science, and it's our great honor and pleasure of having with us tonight Mrs. Monica Herzberg. Thank you for coming. Dr. Herzberg was born and educated in Germany and immigrated to Canada just prior to the Second World War breaking out in Europe. As a physicist, he spent most of his scientific career at the National Research Council here in Ottawa, and it's nice to see familiar faces from the NRC of our colleagues and friends. He was awarded the Nobel Prize in Chemistry in 1971 for his pioneering and influential research in molecular spectroscopy. And as a physicist, he spent among his numerous honors and positions, Dr. Herzberg served as Chancellor of Carleton University between 1973 and 1980. Dr. Herzberg was dedicated to furthering the freedom of inquiry in science and was a strong proponent of the importance and relevance of science to society. It is therefore fitting that the annual Gerhard Herzberg Lecture is typically on a science-related topic of general interest and relevance to the public at large. Over the past 19 years, we have had the honor of hosting a great many distinguished scientists and we have that presented this lecture. We are very thankful tonight that Professor Rolf-Dieter Heuer accepted our invitation to present this year's Herzberg Lecture. But first, it is my pleasure to introduce to you another distinguished guest tonight. Professor Nigel Lockyer is the director of TRIUMPH, Canada's National Laboratory for Particle and Nuclear Physics, located in Vancouver at the University of British Columbia. So right now, I'd like to call upon Dr. Lockyer to come to the podium and introduce our speaker tonight. Welcome.
Feels like a big class tonight. So if you look up on the screen here, you'll see that Rolf is a professor at the University of Hamburg. He's an experimental particle physicist by trade. He has a card that says that on it. And he's the director of research at DAISY. DAISY is one of the premier experimental laboratories doing particle physics and condensed matter physics in the world. It's in Europe. There's about 1,500 researchers there. So Rolf started his career, his undergraduate degree came from Stuttgart University. His PhD came from University of Heidelberg. And he did his work at E plus E minus storage rings. That means positron electron storage rings. The front row's looking puzzled, so you'll have to explain what positrons are, Rob. So after working at the Doris storage ring, which would fit sort of in this part of the room, he then moved on to the Petra storage ring, where they discovered the gluon. That's the particle that holds the nucleus together. At the Doris storage ring, he studied the charm quark. And then after that, he moved to CERN, and he worked at what was then the largest accelerator in the world. It was 27 kilometers in circumference, so it does not fit in this room. And he was in charge of one of the 4 major experiments. Now, interestingly, that experiment, which was called Opal, had about 25% content from Canada. So it was a large Canadian contingent there, and that Canadian contingent was headed by a professor from Carleton University, Professor Carnegie, as maybe many of you know. So there's a number of people here in the audience who've worked with Rolf in the past. They're all, I think I heard they had a wild party last night. And Rolf then, after doing that, went back to DAISY. And out of the blue, he got a phone call one day, and now he's going to be asked to be the next Director General, as they call it, of CERN. That's the world's largest laboratory for particle physics. So The Economist magazine did a spread on Rolf. He's now a celebrity. And it said his position is the top scientist job in the world. So he's the #1 scientist in the world, and you're going to hear from him tonight. Now, you can also read about him in the Lufthansa magazine. I should probably stop there and introduce Rolf. So, Rolf, come in.
Nigel, thank you very much for these nice words, 2 kind words, I must say, and thank you that you stopped at a certain stage. But I can tell you it was, and it still is, a real pleasure to work together with a Canadian scientist, and I do it now since 24 years. So that was always very nice, very good relationship, and I'm happy to be here. I'm not only happy to be here, I'm also honored to be here to give that lecture. So really, I must say, I repeat it, I'm honored. And I'm also not only honored, I'm really astonished and pleased to see all seats taken, except of one. So there seems to be still 1 seat free. Okay, so fine. So let's start. I thought we wanted to dim the light a little bit. Okay, he's coming. It doesn't matter. This year's Herzberg Lecture is about the Large Hadron Collider, shedding light on the dark universe. And I thought before we go into the dark universe, let's see if we can make some connection to Gerhard Herzberg. Well, I think he had, if I'm not mistaken, he had early ambitions to be an astronomer. He was pursuing research related to comets and planetary atmospheres. He investigated planetary spectra by pioneering methods, which at that time were really forefront science. And I guess they are still today. And he and his group studied the absorption spectra of many molecules which were and still are of high interest for astrophysical and astrochemical reactions. So very important. So I would say Gerhard Herzberg shedding light on the visible universe. Okay, so I think that's a connection between Herzberg and what we are doing now. Now what we try to do now is, as I said, shedding light on the dark universe. And the talk will cover 3 topics. Topic number 1, particle physics and the early universe, and I will try to explain positrons, at some stage at least. Then the Large Hadron Collider, and then the connection between the Large Hadron Collider and the dark universe. So, first of all, particle physics at accelerators. It's in principle easy questions which we are addressing. Which are the fundamental constituents of matter? And which forces act between them? These are the 2 fundamental questions we are asking about. And when we investigate the structure of matter, when we study these 2 questions, we can gain understanding of the early universe. And that connection I want to make now. This is the universe, the development of the universe on 1 transparency. Now, unfortunately, we don't have a pointer here. So I have to look up at it from time to time. On the right-hand side, it's 15 billion years. So that is today. On the left-hand side is the birth of the universe, the so-called Big Bang. 1 billion years after the birth of the universe, we had the formation of stars. After 300,000 years of the formation of the universe, we had the formation of atoms. 300,000 years after the birth of the universe, only the atoms were created. 10 to the minus 5 seconds, so 10 millionths of a second after the Big Bang, nucleons were formed. Beforehand, nucleons were not existing. It was free quarks and gluons in a sort of soup, the so-called quark-gluon plasma, which we think the universe existed on. And 10 to the minus 10 seconds after the birth of the universe, so very quickly, forces were separating. The universe was expanding in an inflationary way. And that's the region where we are working with our accelerators at 1 TeV. I will immediately tell you what TeV is. At 1 TeV. And our vision is that with our accelerators, we study the microcosm and will have revolutionary advances in understanding the microcosm. And then we can connect the microcosm with the early universe. And I personally think with the LHC, with the particle physics at the energy frontier, with highest collision energies ever produced by mankind, will change our view of the early universe. And that will happen in the next 5-6 years, so stay tuned. Okay, now TeV. We have this unit which is called eV, electron volt. 1 electron volt is the energy a proton or an electron gets when it is accelerated by a battery of 1 volt. That's it. That's 1 electron volt. That's very tiny. It's nothing. So we have to go higher. The experts know. The LHC, the Large Hadron Collider, will work at 14 TeV. Now 1 TeV is 1000 GeV, which is a 1 with 1, 2, 3, 4, with 12 zeros. I have to prove that I can still count. So the LHC energy corresponds to 2 times 7,000 billion batteries. That means 14 batteries per star in the Andromeda galaxy. If we would do it like this, we would be rather stupid. So we have to do it in a different way. But that's the unit we are using. And the proton, which is part of the hydrogen atom, for example, the nucleus of the hydrogen atom, weighs 1 GeV. So 1,000th of a TeV is the weight of a proton in that unit. Okay, so what is the role of accelerators? First of all, produce high energy in order to be a better microscope. And I will explain why we need higher energy and better microscope. So you resolve the inner structure of matter by using higher energy. And the physics students know that the higher the energy, the smaller the wavelength. And your probe, when you do something, when you probe something, your probe must be smaller than the object which you are probing. Otherwise, you don't find any structure in that object. I think that's obvious. But if you have higher energy, then you are also able to produce new particles because you can produce new particles with higher mass because you cross the threshold with this energy in order to produce these particles. But it doesn't help you if you do it once or twice or so. You need high statistics. You have to do it very, very often. So you need so-called precision measurements. And I want to give an easy example how to understand that. Suppose you have a, Gerald, picket, thank you. Suppose you have a picket fence in front of you. But you don't know that it's a picket fence. And you take a basketball and throw it onto that thing. The basketball always comes back. So what do you conclude? You have a wall in front of you. So your probe was too big. So take a smaller probe, tennis ball or table tennis ball, and then you throw it a few times, many times, and then you can find at some stage the shape of that thing which is in front of you, namely a picket fence. But then sometimes these the pickets? The pickets might have knot holes. How to find these knot holes? Well, you take the head of a pin needle and throw that. But you have to throw very, very often, and then sometimes you can find the pinhole, the knot hole. Okay, so you need smaller and smaller probes and you need very high statistics. And that's all. Smaller and smaller probes means, in our language, better and better microscopes. That means higher and higher energy. So the microscopes have to be bigger, have to have higher energy. And we have to throw, that means we have to collide very, very often in order to get good measurements. Okay, so that's an easy example, and that's all what you have to do in particle physics. So what can we do? We can only accelerate charged particles. Charged particles like electrons and the famous positrons. The positrons are the antiparticle to the electron. So it's like a positively charged electron. And we can accelerate protons and antiprotons. Now, how can we accelerate? Well, we do it like in the battery. We do it through an electromagnetic field, through voltage. And the accelerator size is determined by the technically achievable magnetic field strength to keep the particles on an orbit, because you have to accelerate them further and further. If you do tracks and fields and you do this throwing of a hammer, you know when you turn faster and faster, the force is stronger and stronger, so you have to act against this force, so the magnets have to be very strong. And you have to give the particles energy, you have to accelerate them, and they lose energy in the arcs, and you have to put back this energy which they lose in the arcs, and therefore you have to have a good technology to accelerate particles, and that's another technically challenging subject. The problem is particles are losing energy dependent on their mass. You have this formula up there, E over m to the fourth power. That means the lighter the particle, the more energy they lose. That means protons, which are much more heavier than electrons, they lose much less energy, so you can much easier accelerate them. This is why you can reach such high energies with a proton collider. Okay, so much to the introduction now to particle physics and the early universe. So what do we know about the microcosm? Well, we know that we have matter particles. And these are the matter particles, the up quark, the down quark, the electron, and the electron neutrino. These four matter particles are enough to explain you, me, everything in here, everything what you see. These four particles are enough. The up and the down quark, they form the proton and the neutron. These together form the nuclei. And the electron is needed for the atom. That's all. You see the dots on the left-hand side? These are symbols for the mass of these particles. And I put an arrow on the neutrino because there's a tiny, tiny dot. That means there's a very, very small mass of the neutrino. But that's in principle all what we need. Now nature is more complicated. Nature has created a second family, exactly looking the same. 2 quarks and 2 leptons. The muon is a partner, is the brother of the electron. The only difference between these two families are the masses. So the masses of the particles of the second family are much, much higher than the masses of the first family. In principle, we don't need the second family to explain us. Now, nature went one step further and introduced a third family. And everybody who watches the thing closely knows now what comes. The mass is even higher. It's fantastically high. The top quark, the top one, is a so-called top quark, weighs 175 GeV. 175 GeV corresponds to the weight of a gold atom. And a gold atom is a large object. This thing is a point-like object. We don't know its dimension. We only know its maximal dimension can be 10 to the minus 18 meters. It's point-like, but it weighs 175 GeV. And we have measured very well that there are 3 families. We have done this at this collider, which Nigel mentioned, lab. We have measured the number of families. And you see here a resonance curve. Doesn't matter what it is for the moment. But you see the points, the dots, these are the measurements. And the red curve shows you the expectation for 3 families. Perfect agreement. So there are 3 families. The dotted one is for 4, and the dashed one for 2 families, excluded. So there are 3 families. Why? We don't know, really. And why is the mass so different between the different generations? We don't know. But we will find out. Oh, this thing is very sensitive. Okay, so this is structure of matter number 1. The matter, stars and the living organisms, consist of 3 families of quarks and leptons. Now, matter around us, as I just said, we only need family number 1. However, at high energies, close to the Big Bang, matter is democratic. And all 3 families are present or have been present at the time. So if we can create situations for a fraction of seconds after the creation of the universe, that means if we study the matter at high energies, we learn something about the early universe. And that's a connection between the microcosm and the macrocosm, the early universe. Now, these particles have to interact with each other. Okay, so you need forces, and there are 4 forces in the microcosm. One is gravitation, which acts on mass and energy. The other one is electromagnetic force, which acts on charges. Without that force, you wouldn't have any atoms. Then you have the so-called weak force, which acts on leptons and quarks. That means on all of these particles. It's the only force, except for the gravitation, which acts on all of these particles. And it's responsible for the reactions in the sun, for example. So without that force, we couldn't live, because the sun wouldn't shine. And then the strong force, which acts on the quarks, and which binds the quarks together into the nucleons, and then the nucleons together in the nuclei. So without that, you wouldn't have any nuclei. So we wouldn't have atoms, nuclei. So we need all 4 forces. And these forces are exchanged between the matter particles by so-called force carriers or gauge bosons. Gravitation is exchanged by the graviton, we think at least. We know that the strong force is exchanged by the gluon, the electromagnetic force by the photon, and the weak force by the so-called W and Z bosons. And that we all have measured and we know. And the interesting point is that if you look onto the second column here, the relative strengths of the types of forces, the strong force, electromagnetic, weak, and gravitation, if you normalize it to the strong force, then you see the electromagnetic is much less powerful than the strong force, the weak force even less powerful, and the gravitation is essentially non-existing at our energy range. This is in our energy regime. That means in the regime we know. The force carriers I have listed again, and one remarkable thing is that all the force carriers have mass equals 0, except for the W and Z bosons, which weigh 80 or 90 proton masses, 80 or 90 GeV. And they act on different things, like strong force acts only on the quarks, is responsible for the nuclei, as I said. Electromagnetic force on electric charge, so forms the atoms. Weak force acts on all the particles, and gravitation acts on mass and energy. And in the microcosm, we just neglect the gravitation. Anyhow, we have problems explaining it there, but it's so weak we can neglect it. Sometimes we make our shortcuts. No. Okay, so 4 fundamental forces act between matter particles through the exchange of these so-called gauge bosons. And within our energy regime, I have shown you that the respective strength of the forces is vastly different. Really very, very different. Now, if you go to high energies, the forces become more and more equal. That means the question is there at the beginning of the universe only one force which afterwards separates into the different forces? So if we create again situations, fractions of seconds after the Big Bang, And if we can study the forces of nature there, again, we get knowledge about the early universe. So that's another connection between microcosm and the early universe. Okay. So that's the static model of particle physics, the standard model. The physical world is composed of quarks and leptons, which interact via force carriers. And that is all what you need to know. The three families of quarks and leptons and the force carriers. Great. It would not be so great if that would be the end, because then I wouldn't stand here. Okay. Now that was a static model. Now we have to explain the dynamics between the of the forces and of the particles. So we have the so-called standard model of particle physics. This is a mathematical formalism, which I will not explain, which describes all interactions which are mediated through the weak interaction, the weak force, the electromagnetic force, and the strong force. We neglect the gravitation, as I said. And we have tested these predictions of the standard model with very, very high precision. We have validated it experimentally up to the accelerators we had up to now, let's say 100 GeV, which corresponds down to a structure of the matter to 10 to the minus 18 meter. So this is 0.1801. That's quite a bit. Now that looks complicated. Actually, it is. But it's not as complicated as it looks at the beginning. Look, these are several measurements. It doesn't matter what type of measurements. And the measurement is compared with the prediction of the standard model. Now, every measurement has an error. Now, if the measurement lies top on the zero, then it's exactly on the standard model prediction. Now, if you normalize the error, then number one means one standard deviation error away from the standard model. 2 means 2 errors away. 3 means 3 errors away. If you do many, it's a distribution which you expect. And if you do many, many measurements, you need to have, if all your measurements are done correctly, you need to have deviations of 1, 2, and 3 error bars. So that thing is absolutely normal. Actually, without this large deviation of 3 standard deviation, the fit would be too good. So we need such a deviation. So it's fantastic. The thing has been tested to fantastic precision. Great. What a pity. There's one piece missing in the standard model. And that's the question, what is the origin of mass of elementary particles? I have shown you the huge difference between the masses of the quarks. I've shown you that the W and Z bosons have a mass, high masses. The standard model, when it was invented, even the inventor said, it's great, and we know that it works only for massless particles. We also know that particles have mass, but it's such a fantastic model. Let's ignore the mass for the moment, which they did, fortunately, because then a few years later, the physicist Peter Higgs, together with 2 other physicists, Brown and Englert from Belgium, he introduced another field, another mathematical formalism, which you could add to the standard model formalism, which then allowed the validity of the standard model to stay, but also to be valid for massive particles. So the 2 things together allow the standard model to explain massive particles. So this is the so-called Higgs field. And many of you might have heard that we are hunting the Higgs particle since many, many years. The Higgs particle is a particle which follows naturally out of this field, because this field must have a self-interaction. That means it has to create a particle by itself. And this particle we have to find, and if we find it, then we know, then we have found the Higgs mechanism which gives particles a mass. And Mr. Nambu, who got half of the Nobel Prize this year, he was laying the foundation for this theory here. And Peter Higgs got inspired by Nambu. And so if we find the Higgs particle, then Higgs will get the Nobel Prize. And we know, okay, yeah. So I told you self-interaction giving mass to particles. How can I illustrate that. Now, okay. Suppose you have a party of journalists. The cold buffet is empty, because if it would not be empty, they would all be at the cold buffet. Now they are distributed more or less equally in the whole room. And now a particle comes in from the left-hand side, which is a famous particle. And this famous particle wants to go through the room with the speed of light, because then the particle would have mass equals to 0. Unfortunately, that particle is relatively famous. It starts interacting with the Higgs field. So the journalists cluster around that particle. The particle gets slower. It acquires mass. And the more famous the particle is, the higher its mass. So a completely unknown particle just goes through with mass equals 0. The higher the more famous you are, the heavier you are. That's all. That's the way you get mass to particles. Okay. So how to explain the self-interaction? Well, there's somebody whispering a rumor into the room. And journalists are quite interested in rumors. Sometimes they even publish them. Okay, and that's the Higgs particle. They cluster around. What did he say? That's the Higgs particle. Yeah? And you see, the analogy is very nice because the Higgs particle moves through the whole room. It's sometimes on the left-hand side, sometimes on the right-hand side. So the Higgs mechanism is nothing else than this in formulas. And I don't understand the formulas, but I understand that analogy. Okay, so you see, particle physics is really easy. And it's fun. Now, the Higgs particle, I said, is the last missing cornerstone of the Standard Model. And we know everything about the Higgs particle. We know everything. Only one thing we don't know. Does it exist at all? Okay, but we know that we need it if the theory is correct. That means we will find it if the theory is correct. If we don't find it, the theory is wrong, but then we find something else. Yes? Sure. So the question is, does it exist at all? And that we will come to later. Okay. Unfortunately, the Standard Model explains so many things, but unfortunately, it leaves so many things open. There are a lot of unanswered questions, and I don't want to go through all these unanswered questions. These are only there for the physics students. I want to concentrate on the two red ones. What is dark matter, and what is dark energy? The Standard Model doesn't have any clue. We also don't have much clues. Anyhow, but the Standard Model doesn't explain anything about it. So why is it so interesting? Look at it. I mean, we have studied 40 years the Standard Model. But the yellow stuff on the top, it shows you the Standard Model explains roughly 5% of the universe. 5%. The rest, the 95%, are to 1/4 dark matter, the right-hand side, and to 3/4 the so-called dark energy on the left-hand side. Dark matter is like normal matter, but it is very weakly interacting. That means we don't see it. We only see its effects through gravitation at the moment. And it clumps. It is like normal matter, so to speak. It clumps. It has gravitation, yeah? The dark energy is the contrary. It is not an energy. It's just a name, dark energy, because people didn't know how to name it. But that thing is driving the universe into expansion. It expands the universe. So it is counteracting the matter, so to speak. And that's responsible for the expansion of the universe. And it doesn't have any direction. It's in physics terms, it's called a scalar because it doesn't have any direction. The universe expands in all directions. That means there's no particular direction which it will go. We don't know very much about dark matter. We know much less about dark energy. But one thing we know is that with the Large Hadron Collider, at the TeV, the so-called Terascale, TV scale. We can now enter the dark world. I think we are about to enter the dark world, to shed the first light onto the dark world. Okay, that brings me now to the Large Hadron Collider. And I have no idea how well I'm doing in time. Badly. Okay. Okay, we get through. Okay, the Large Hadron Collider is at a very nice region, the region of the Geneva Lake in Switzerland. And you see, if the light, I don't know if one can see it, that's a top view of the region. You see the Lake Geneva on the left-hand side, the Alps, the airport, and the red ring is the 27 kilometers ring of the LHC, where beforehand the lab ring was in. So this is also why it's 27 kilometers. This one is very sensitive. It is the largest scientific instrument ever built with 27 kilometers circumference. Some people say it's the coolest place in the universe. I'm a bit more cautious. I'm saying it's the coolest ring in the universe. Minus 271 Celsius, that means 1.9 Kelvin above the absolute zero. Pretty cold. 10,000 people roughly were involved in its design and construction with a worldwide budget over 10, 15 years of 6 billion euro. It collides protons to reproduce the conditions at the birth of the universe, and it collides them 40 million times a second. It's quite often. So 70 eV protons on 70 protons, 70 eV protons. Highest collision energies ever achieved by mankind. It creates conditions 10 to the minus 10 to 10 to the minus 12 seconds after the Big Bang. 4 large experiments we measure there. As I said, constructed in worldwide collaboration, and it started summer 2008 with the first turn of the protons. It took 25 years from the first paper, 1983, about the possibility of such a machine until today where we can switch it on. It takes a long time. It creates many gray hairs, but it's a fantastic project because you go through all the phases of the project, and the students can learn a tremendous amount of it. Not only particle physics, also high tech. It's a high tech thing. It's technology at the forefront. Okay, the rest is for. So, April 2007, the last magnets went down, and there's only one shaft which is big enough in the 27 kilometers which allows to put down the magnets. You have to put down 1,232, if I'm not mistaken, magnets. And that means in total you have to, and then you have to fill the ring. You can only drive slowly with these 18-meter long magnets, so only at 2 kilometers per hour. So in total it was 30,000 kilometers underground at 2 kilometers per hour. Now everybody who can calculate knows that this is not being done in a few weeks. So that takes years already. It takes years to do the research and development. It takes years to build it, and it takes years to run it, and it takes years to analyze it. That's why it takes so long. Okay, so there are people connecting the magnets. Okay, so the protons are bunched in packets. You see it on the left-hand side, and in the red ring they run clockwise. Yes. In the blue one, they run anti-clockwise, and then you bring them to collision at certain points. Once everything runs, nearly 3,000 of these packets running through each ring. So we have collisions every 25 nanoseconds because the distance is 7.5 meters between the bunches of packets. That makes 40 megahertz crossing rate, 40 million times per second. Now, if one reaches design value with 10 to the 11 protons per packet, then you have, because you have strong interaction, 35 interactions per crossing. That means you have 35 times 40 megahertz, 10 to the 9 interactions per second. 10 to the 9 interactions per second is a lot to register. So in each collision, more than 1,000, roughly 1,600 charged particles are being produced. That means you have per second a tremendous amount of charged particles, which you have to measure. It's an enormous challenge also for these detectors which should measure these particles. Now that thing was too fast, so I have to be very careful here. Okay, so again, this is a 27-kilometer ring, and now there is the 4 experiments, the 4 big pictures, and now I concentrate on the top one, CMS, and the bottom one, Atlas. They are multi-purpose experiments, and they are rather large, because you see on the bottom right-hand side of CMS a lady, and here you see a couple, and that shows you the dimensions. These are huge experiments because you have large energies. That means that you have, in order to separate the particles, you need large experiments. By the way, the C in the top one stands for compact. You will see why. Okay. Now let's go to Atlas. I don't have time to explain how an experiment is looking like, but it's like an onion. You have several layers of different types of detectors which serve for different types of particles. So in principle, it's always the same concept, but with different and very high developed technologies. That should give you an impression that particle physics is not only research, but also art. This is a fantastic picture. Unfortunately, that's only the beginning of a building of such a detector. Once the detector is constructed fully, you only see a closed box. So it's much more interesting when it's being built and you see an average human being here in the middle. Now you see, now it's much more filled. It starts becoming crowded, and this part here, the top one, is rolled in on a scaffolding here which is in red, in order to be inserted. And if we focus now more onto the inner part here, you see that part, which is a component from Carleton, which was constructed here, which is just being inserted into the detector. And there was, a few years ago, when it was inserted, a happy assembly team at Carleton around one of the detector parts. It looks very small, but it's a very important inner part, very sophisticated technology. And most of the people are looking pretty happy. Some in the background not, or I'm not sure why. Okay. Okay. Now, this is a 5-story building at CERN, and you see Atlas is roughly as big in diameter as a 5-story building is high. And now you understand why CMS is a compact detector. It's much smaller. It's still big, but it's compact compared to Atlas. Now, these experiments take about each one has about 100 million sensors which record the particle tracks. And you have to think about your 6 million pixel digital camera taking 40 million pictures a second. So these things take 40 million pictures a second with 100 million sensors. Tremendous amount of data. That's also a challenge. Okay. And this tremendous amount of data comes because there's a huge cross-section, which is at very top, I think it's black line, which is the total cross-section. That means the total rate with which you produce particles. The interesting thing, this is a logarithmic scale. The interesting cross-sections are the blue ones, the Higgs, for example. Take the blue or violet or whatever it is, the blue one from the bottom, the second one, which goes like this. It is, I think, 10 orders of magnitudes below the total cross-section. So in order to find particles which are produced at this very small rate, you have to dig them out of a huge rate. It's like a needle in a haystack. If you start searching for a needle in a haystack, I mean, that is a bit stupid. You know it's a needle, so you take another instrument, like a magnet or so. So we do the same. We don't use magnets, but we use sophisticated computing programs to dig out the interesting events, interesting cross-section out of the total cross-section. But that we will do. So what we have to do is we have to use online computer filters which use the 40 megahertz rate, and then reduce it to a few hundred good events per second. And even if you have only a few hundred good events per second, we expect to record 15 petabytes per year for all the 4 experiments. This is, if I'm not mistaken, more than all the data of the telecommunication in the world. That means you have to phone even more in order to reach that. This is a lot. Okay, and this gives you a visual impression. It's old technology, I know. Nowadays one does do DVDs. But if you take CDs, then a stack with 1 year LHC data would be 20 kilometers high. So that, of course, you cannot do just at one computing center. So the idea is, I mean, the World Wide Web was born at CERN 17 years ago because we needed the distributed information exchange, fast access to information. Now we need distributed computing power, fast, etc. So it is like, again, like an onion. You have the nucleus at CERN with a large computing center. You have several layers of other computing centers worldwide around it, where the data are distributed to and where the programs are running. You cannot do that at one place anymore. So it's the so-called grid, which is in red here, which is a sort of computing out of the plug, at some stage at least. So that might revolutionize the computing world, similar as the World Wide Web did 17 years ago. Okay, now we come finally to the science. What is mass? Why is there more antimatter than antimatter? And what is 96% of the universe made of? Okay. Now with all this preparation, I think we are now ready to enter the dark world, the dark universe. Let's first start with dark matter. Well, astronomers and astrophysicists will tell us in the next, I don't know, 10, 20 years, how dark matter has shaped the visible matter, the stars, the galaxies, etc., which we see every night in the sky. Of course, it has shaped it, must have shaped it, because it's also matter. But only particle accelerators are the only tool that you can hope to create dark matter particles in the laboratory. And once you create them in the laboratory, you can study them, and then you can see, is dark matter composed of a single kind of particle? Or is it more rich and more varied, similar to the visible world? Would be very interesting. And LHC may really be the perfect machine to study dark matter. Why? Well, sorry about the German transparency, but this is a PDF and I cannot change PDF. So the favored candidate nowadays is the so-called supersymmetry. Supersymmetry creates a new world with respect to the known world. The known world is on the left-hand side, and whoever is still awake remembers that is the particle, the microcosm, with the 3 families, with the force particles, and with the Higgs particle now. On the right-hand side, you have the new world, the so-called supersymmetric world. Now you can say, okay, when physicists don't know any answer anymore, they just create more particles. It's an easy way out. It's a slightly different. Remember when Dirac introduced antimatter, with one formula, he created a factor 2 in the number of particles. He doubled the number of particles. And what amount of knowledge we have gained through that. Fantastic. Here, it could be very similar. We could gain a tremendous amount of knowledge by doubling the number of particles. So why are we doubling the number of particles? Well, each particle in the known world gets a so-called supersymmetric partner in this other world. A matter particle in the normal world gets a supersymmetric force partner in the supersymmetric world. A normal force particle gets a supersymmetric matter-type particle. So you get a symmetry between force and matter particles. This is why it's called, I guess, why it's called supersymmetry. So that creates something very new for particle physics, because we were always bothered why are particles, matter particles and force particles different in their behavior. So here you symmetrize it. Supersymmetry would allow to unify forces at the birth of the universe, which you could not do in the dashed part, which is a standard model. You can do it with supersymmetry. And in many, many supersymmetric theories, the lightest supersymmetric particle is stable. Stable supersymmetric particle would mean dark matter candidate. This is why it's a favored at the moment, really the favored theory. Okay, now there are many models in supersymmetry, and you need data in order to constrain the models and to see which model is the correct one. And that is just one model example. Here you have the supersymmetric partner of the quarks, of the leptons, of the gauge bosons, the force carriers, and of the Higgs particle. And on the vertical scale, you have the mass in GeV. And these would be all in the energy range of the LHC. So if they exist, you should find them. Of course, there are other models where they are lying much higher. It's more complicated. But supersymmetric particles could be identified at the LHC. You have proton-proton colliding there. You create new particles, for example, supersymmetric particles. And they, along this chain to the right-hand side, they decay into normal particles plus another supersymmetric particle. And that goes down until the phase space is taken off. And at the end, you have only the bottom particles, so QQLL in this case, which are the normal particles, which you see in your detector. And on the top one, the so-called Chi-0 which would be the lightest supersymmetric particle, which would be stable. And since it's not interacting or only weakly interacting, it just goes out of your detector. You don't see it. So what does this mean? You measure the normal particles, and you measure something which is not there. That means you measure missing energy, because you're missing a particle, and missing momentum. And that's the signature with which you would identify supersymmetric particles. This is illustrated in this middle plot here. You see the beam pipe where the protons are running against each other, meeting in the middle. And the blue and red are the visible particles. And you see they are in this example, which is well chosen for that purpose here, of course. You see they are all on the right-hand side of the beam pipe. On the left-hand side, there's nothing. There's missing energy. That would be a signature for supersymmetric particles. So the key is missing energy, missing momentum. But the other key is you have to well understand your detector. Because if parts of your detector don't work, you don't see any signal in that part. And you better know that before you publish that you have made a discovery. Okay, and then you can measure the I have two microphones. I mean, one for him and one for him. You can measure the mass of the supersymmetric, of the lightest supersymmetric particle, and then you have data from satellites, WMAP and Planck, and on the left-hand scale you have the fraction of dark matter density, and they can measure the dark matter density, but they cannot measure the type of dark matter. So this is why there is a line or a slot from left running to right. And in the middle, you see the blue or greenish box. This would be if the LHC finds a supersymmetric particle which agrees with its properties with dark matter, and it would lie on top of this line, and then you would have an indication that this particle is responsible for the dark matter in the universe. If in the insert, the box is not coinciding with the stripe, then the dark matter world is more rich, more varied. Then you have only found part of the dark matter. That would be even more appealing. Okay, so with the LHC, you can really get the first glimpse on dark matter. Maybe you can even definitely find dark matter. Okay. LHC results should allow, together, of course, with dedicated dark matter searches, which are also existing, first discoveries in the dark universe. Okay, but still, 73% of the universe is in some mysterious dark energy. This is evenly spread in the universe, and it exerts a negative pressure. It's responsible for the expansion of the universe. So the real challenge is now to get first hints about the world of dark energy in the laboratory. And this is, I can tell you, everything up to now was easy. This will be really difficult. But I try to make a connection. You remember? I told you the Higgs particle. I haven't talked about the Higgs particle yet. The Higgs particle, I told you, in our language is a scalar. It doesn't have any direction. Or the Higgs field, sorry. The Higgs field doesn't have any direction. So it fills the entire universe. So does the dark energy. I'm not saying that the Higgs particle and dark energy is the same. I'm not saying that. Don't take that home, because that would kill all my reputation. But the Higgs is just different. All matter particles, I told you, are one type. It's spin half fermions. Doesn't matter what that is. They have a spin. They have a rotational symmetry. All the force carriers are spin 1 bosons. The Higgs particle is spin 0. It doesn't have any spin. It is neither matter nor force because it doesn't have a spin. It is just different. And if we find the Higgs would be the first fundamental scalar particle ever detected and looked at. And the Higgs field, as I said, is thought to fill the entire universe. The dark energy is supposed to fill the entire universe. So both are scalar fields. So when we are able to find the Higgs, and when we are able to study the properties of the Higgs, maybe we find some idea about the properties of dark energy. We couldn't possibly make that connection. I have shown that several times to other audiences with theorists in, etc. Nobody has killed me up to now. So I think this connection might really be there. And that would be just great. That would be something completely unexpected because nobody thought we could find anything about the dark energy. But the LHC can search for the Higgs and also for other scalars if they are, and study them with precision. And that could give some idea about dark energy. And this is complicated or easy. This should tell you that if the Higgs boson exists, it will be found at the LHC. Why? On the left-hand scale, you have the Higgs mass range, which is allowed for the Higgs, which was 1996, when these data were analyzed, very large, between 0 and 600, 700 GeV. Now, with taking new data, analyzing new data, etc., you go from the left to the right, and you see with better precision measurements with our accelerators, the range of the Higgs mass, which is allowed, is now much smaller. It's between 100 and 200 GeV. This is an easy energy range to cover by the LHC. It is not easy to find the Higgs in that range. It's actually the most complicated mass range to find, but it will be covered, and if it exists, we will find it. But it will take some time, as this one does. Okay. I don't think I go into details here. People can ask me questions what the plot on the right-hand side is. I don't go into that now. But how would you find the Higgs? Well, you would study and combine particles which you find in your detector, and then you would combine it kinematically to some resonance signals like here on the right-hand side with less background, with much background. And finally, if you combine everything, after a few years, with a lot of statistics, you might have found the Higgs. And what can you do then? Well, then you measure the reaction of the journalists with the famous person. That means you measure the coupling of the Higgs field to the other particles. And this is a plot how you would do it, which I don't want to go into detail again, but that plot is the important one. Here you have the coupling of, for example, the charm quark, tau lepton, B quark, WZ on the top right-hand side. The coupling as a function of the mass of the particle. And if it follows the yellow line, then you have found the standard model Higgs. Because then it's responsible for creating mass to the elementary particles. If it doesn't follow the yellow line, then you have found something else, which is also great. And you continue searching. But this is the decisive plot at the end to say, okay, it's the Higgs mechanism which gives mass to elementary particles. Okay. Now this thing is running out of power, so are you and I. Okay. LHC results will allow to study the Higgs mechanism in detail and will allow to reveal the character of the Higgs boson. This would be the first investigation of a scalar, fundamental scalar field. And this could be the very first step into understanding dark energy. So, the past decades, and I had 40 years on there, the past decades in particle physics saw the precision studies of 5% of our universe. It was the discovery period of the standard model. The LHC will soon deliver data, somewhere next year to start. I think we are just at the beginning of exploring 95% of the universe. The future is bright in the dark universe. Thank you.
Large theater, and I'm we have two microphones here.
For the moment, I guess everybody is exhausted. Oh. If you can also, I can repeat the question if it's easier.
What's the alternate mechanism to Higgs if you can't find Higgs?
The question is, what is the alternative, the alternate mechanism to the Higgs mechanism? There exist several theories. There could be another strong force acting between the particles, which would show up in the energy range of 1 TeV, for example. That's one possibility. Composite particles is another possibility. But since the standard model is so fascinatingly well doing, everything else what you invent has to agree with the measurements up to now. So it's very difficult to find something plausible outside the standard model. But theorists have a lot of ideas. There are a few around here that can tell you much more. But these are two examples. Yes?
If you were to turn on the machine tomorrow, what would you like to find?
Dark matter candidates. It's more fascinating for me than the Higgs. The Higgs is meanwhile so standard, maybe because I'm used to it meanwhile, I don't know. Yeah. Supersymmetric particles would turn me on, but also the Higgs, of course, yeah. Fortunately, it's not up to me. Fortunately, it's up to nature. But the main thing I want to do is to switch on the machine as soon as possible. Yeah.
Sir, I'm actually an art student, so I don't really know anything about physics or engineering at all.
Okay, so ask an art question.
Yes. It may be a little off topic, but I've heard rumors that there's a chance that this could create perhaps maybe a black hole or some other event that would not be very good for humanity as a whole. Are there any dangerous outcomes from the LHC?
There's a very simple answer, which is no. But I tell you why, because I mean it's easy to say no. I tell you why, and that's pretty easy. There are theories like this, and it could happen that one could create mini black holes. They have nothing to do with the black holes in the universe, completely different. There are many theories, but what convinces me as experimentalist, sorry to say to the theorists, but what convinces me is experimental facts. And what is the universe, what is nature doing? Since billions of years, it bombards us and all the other stars, all the other matter, with particles which have even higher energies than we can ever create here at the LHC. So it happens billions of times per year over billions of years. And we are still talking to each other. Okay? And that convinces me. So the answer is a clear no. That's an experimental evidence. There's one. Oh.
Do you think it's possible for us to ever fully understand the universe?
The answer is clear, no. I really don't think so. We are coming closer and closer, and the more we know, the more also we know to pose other questions, more detailed questions. But I don't think that we will finally get the ultimate answer. This is tremendously difficult. Compare it to the picture which I showed of the universe, where everything, I mean, in the very first billions, then I don't know what the next thing is, trillions or whatever, seconds, a tremendous amount has happened. And this you have to explore. I don't think we come ever to the very end. I think it would be boring if we would come to a very end. No, I don't think it's possible. But it's not frustrating. It's fantastic. You learn more and more.
Thanks. Have we created particles on Earth that haven't been in existence since the beginning of the universe?
Oh, they are still existing partly. I mean, look, these suppose supersymmetric particles would exist. They exist also in the universe. But we can't find them because the reaction rate is so small, and they react so little with the Earth, like neutrinos. Yeah? The time we are talking now, we are traversed by thousands and millions of neutrinos, and nothing happens because they interact very, very weakly. So these particles also can be created in these high energy collisions, but then they decay immediately again. So it's a coming and going in the universe. So it's the same particles as are created in the universe around. We don't create anything new. We only learn something new about it.
I'll bring it over.
I don't know.
All right, go ahead. Since space is infinitely expanding, would you say that the dark energy in space could actually have an infinite supply? And if so, is it possible that the infinite mass of black holes is possible because of some convertive process that would alter the matter going into the black hole into dark energy?
Well, since I don't know what dark energy is, I don't know if it has an infinite supply. I actually don't know how the whole thing is run by the dark energy. I really can't answer that question. And on the black hole. Black hole has nothing to do with dark matter. Black hole is ordinary matter. Black hole is the remnant of a big star which has died. The big star only exists because it has radiation, which acts against gravitation. When the big star dies, it collapses because of gravitation. And then you just have this tiny little matter where even no photons are getting out because the gravitation is so strong, but that has nothing to do with dark matter or dark energy. So from that, I think nothing is coming to dark energy.
Hello?
Yes.
Sir, I have a simple curiosity. Can I ask a question? You know, when a balloon expands, we fill in with gas, it bursts. Now you say that universe is expanding, so will it also burst at one stage?
Will it also?
Will the universe also burst at one stage?
Well, to some extent, it's bursting already now. It's expanding, but you don't know where it is expanding. I don't think that's a good analogy with bursting. It's an open space. In an open space, nothing can burst, unless we have another large dimension in which we live and we don't know. So it's just expanding. Actually, I personally have also difficulty to imagine all these things. It's not so easy, but bursting, I would say, is the wrong analogy.
Do you know if anyone has yet made an accurate, reliable measurement of the mass of the neutrino?
Yes and no. No, there have been many attempts and accurate measurements, but these are only limits. And therefore, yes and no. Yes, accurate measurements, but no real value, because only limits have been achieved. Because the masses are so low, it's extremely difficult to measure it. So it's only limits. Okay? Yeah, but that's the case. There are huge experiments now being built in order to pin down the mass of the neutrino further. Yeah.
Hi. Can you give any personal insights on how you think or know the repair works going on right now and when they will complete?
Well, first maybe one should say that there was an incident that something broke at the LHC, which is pretty normal because this is an instrument at the technology frontier which is, so to speak, its own prototype. So that something breaks is quite normal. This is a machine at 1.9 Kelvin. That means and a large mass. That means already in order to have access to the point where something happened, it takes 3 weeks to warm up and later 3 weeks to cool down. In between, you have to do all the repair work, and the present estimate is that it will not restart before beginning of May. But that's normal, again, because all the pre-injectors, the pre-accelerators, which I haven't mentioned, which you also need in order to put the particles into that big machine, they have their normal shutdown, which ends in April. So the hope is to do everything in the shadow of this shutdown. That's the hope. But my statement is not before. I'm not giving an exact date. I'm saying not before. It's difficult to predict such things. It's a new thing. You might find other things. And then we have to make sure that it doesn't happen again.
Can the LHC provide some light on the string theory, or?
It could provide some darkness on string theory. In cases where the string theories rely on low mass supersymmetry, and if we don't find the low mass supersymmetry, then these theories are in trouble. More I don't expect from the LHC. That's, these superstring theorists are very clever. Very difficult. Yeah, they are. It's very difficult to test some of the predictions. So you can possibly exclude some of the theories, but I don't think you can help verifying some of them. I'm not saying verifying, but at least having the first step for verification.
This is a bit of a two-part question. First part, I was wondering, Are those 4 experiments you said, are they all looking for the same thing or looking for different things?
My usual question, my usual answer, yes and no. Okay. The 2 big ones, Atlas and CMS, are, as I said, multi-purpose detectors, which look essentially at the same type of questions with different tools. But that's similar in astronomy. You have different types of telescopes, etc. And so you need you better have different tools in order to study things. So these 2 look more or less at the same questions. Then there's the third experiment looks for matter-antimatter difference. So that's specialized to try to help to understand why we are here at all. Because at the beginning of the universe, matter and antimatter should have been created in equal portions. But there's a tiny, and I don't know how many zeros, I don't remember, many zeros, a tiny, 1 in a billion. Okay, thank you. I have my people in the audience, that's very kind of you, Nigel. 1 part in 1 billion more matter was at some stage in the universe, and that's us. The rest is annihilated because matter and antimatter annihilate each other. But that 1 part in a billion, that's us. And we want to understand why we are here. And this is one of the experiments is trying to address that question. And the 4th experiment is specialized on a completely different type of question. This is, I mentioned at the beginning, the so-called quark-gluon plasma, 10 to the minus 5 seconds after the Big Bang where it disappeared. This quark-gluon plasma, to investigate that, that's the 4th experiment.
And the second part is, I was wondering if you could use the experiments to verify each other,
yes.
Or would you have to create an even bigger Hadron Collider?
Yes and no. Sorry, but it's true. It's true. Yes, of course, we use the experiments to cross-check each other. I mean, if you have a scientific result published, you better cross-check it. There have been many results published which afterwards have been falsified. Okay? So yes, they can cross-check each other. And the no is whatever we find with the LHC will tell us which type of accelerator will be the next type. And one thing which I could not cover here is, here we collide protons with protons. There's another type of collider which collides electrons with positrons. And they are very, very different, but addressing the same questions. Again, looking with a completely different instrument on the same questions gives you much more information. And the plots I showed where we are today, we would not be there without both types of colliders. So this answers is the explanation of the no.
Given what you said earlier about how the internet was developed at CERN based on the...
No, not the internet.
Oh,
the World Wide Web. That's a huge difference. The internet is the hardware. The World Wide Web is the software package. That was developed.
Well, given that it was initially started at CERN, do you see any new technologies being developed that are potentially unrelated to particle physics?
Oh, yes. There the answer is a clear yes. Well, first of all, I mentioned the grid, which is one possibility, which is a new approach for using computing technology and computer power, which could be at some stage useful for the general public. Then the development, accelerators, for example. There are around 20,000 accelerators in the world, mainly in hospitals. And they come from particle physics. And there are roughly, I think, 2,000 per year newly built and sold to hospitals and to ion implantation, to produce radioactive isotopes for medical applications. So that is one thing which comes out. Then we develop new detector technologies. And again, in medicine, it's used now in positron emission tomography, PET. This is using modern silicon detectors, which we have, we took part in the development. And I cannot say that we only developed it, but we took part in it. So this detector technology spills out into other areas. So there's a lot. I can tell you even more.
Given that, as you said, calling dark energy and dark matter is a little ambiguous because we don't really know what they are. What are the differences between dark energy and dark matter? And if we explain one, will that likely also explain the other?
The answer to the second part is a no. The answer to the first part is that dark matter is, in its gravitational behavior, the same as normal matter. Yeah? If you have dark matter, it clumps, it forms, I don't know, it forms maybe galaxies, it may form thick stars or God knows what. It clumps like normal matter because it undergoes gravitational forces. Dark energy is something which I don't know, which really is a mechanism which pulls, what word did I know? Did I take? Which pulls it doesn't pull it. It drives the universe. It helps to expand the universe. So two completely different things. Yeah. And therefore, I don't think if we know something about dark matter that we learn something about dark energy. Completely different things.
When you build a system as large as the LHC, you've got your expected challenges. What were some of the more interesting unexpected challenges that you encountered?
I don't really know. No, that's true, because I don't know what the people expected or didn't expect when they started. I think the unexpected challenge was to keep it more or less on budget. I would say that was maybe the biggest unexpected, or maybe it was even an expected challenge. I don't know. I think the incident which happened on the 19th of September was a bit unexpected. And the challenge now will be to make sure that it doesn't happen again. It's difficult to answer. There were certainly some small things, but on the large scale, I don't think there was something unexpected.
Could you please mention some observable phenomena that can't be really explained without the introduction of dark matter or dark energy? Thank you.
I must admit I didn't understand the question fully.
Are there any observable phenomena that we can measure and they are not explainable by the without the introduction of dark matter or dark energy?
Well, the rotation of galaxies cannot be explained by the visible matter only. The rotation speed of galaxies, well, you know that's normal mechanics, so to speak. You cannot explain by the visible matter which you see in these galaxies. You need something else in addition. That would be dark matter. That's one example. Yeah. Dark energy, the expansion of the universe, that it accelerates, at the moment at least, that cannot be explained without dark energy. Now, there are certainly people who have a theory which is different, but the most probable theory cannot be done without the dark energy. These are two examples.
If the universe is infinite, where does it expand to?
Into the infinite. What else can I say? I really don't know. I really don't know. I mean, it's difficult to imagine. Yeah? I know it's difficult to imagine, but we can only measure, and then we see it expands forever. I don't know where, into the infinite. Maybe in 10, 20 generations, people know more. I don't know. Unanswerable question. So. No. 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 Oh, I should repeat the question. He is asking if he can accelerate himself faster than the speed of light. No, I know, I'm joking. He was asking if the universe can expand faster than the speed of light, and the answer is no.
I have two questions. One is practical. What is the life cycle for this Large Hadron Collider? And how do you envision new experiments coming online? The other one is sort of less practical, I guess, is we're talking about particle physics, reductionism, and how far can you take reductionism as a concept or a theory?
On the first question, the life cycle of the Large Hadron Collider, that means taking data, doing the analysis, etc., I expect 15 to 20 years. Yeah? That doesn't mean that only in 15 or 20 years first results will come out. There's a continuous data taking, continuous analysis, continuous output of scientific results, etc., etc. It's not like that you do one experiment and that's it. You do hundreds of experiments at the same time, and that you do over a long period because you remember the picket fence. You need statistics. Yeah? And for some of these things, you don't need much statistics. For others, you need a lot of statistics. Other experiments coming online, difficult. You have to build such a huge experiment. And you have to find funding. You have to find people. You have to have ideas which make these experiments different to the ones which are existing. So I would say very difficult. Very, very difficult. And the hypothetical, on the reductionism, if I understand what you mean, I think we have reduced the number of observables, the number of particles, the number of parameters already quite a bit. We have to reduce it again if we find supersymmetry. But the ultimate goal is to reduce it to the minimum number which you have. I think that was that the question which you guess? Okay, if you guess so. Well, we want to explain everything with the least amount of equations and with the least amount of parameters. That's what's our goal. And look in the standard model, we have just 4 times 3 particles, plus the antiparticles, plus the force particles and the Higgs boson. That's already pretty small amount for this variety of people here.
I hope this question makes sense.
I don't. Okay.
How do you account for the influence of the observer on these types of measurements, and does the act of observing actually influence the outcome of the experiments?
No. No, the answer is a clear no for the second part, because these experiments have roughly, per experiment, 2,000 scientists on it, which is a sociological experiment in itself, by the way. So they control each other, and they rely on each other. Not one person can do everything from the bottom to the top. So there are many people in the chain, there are many different groups analyzing, so there is a constant cross-check. So I think the personal influence is very close to zero. You don't believe me? It is like this. It's a huge amount of people working on a very complicated thing. Of course, you cannot exclude errors, but then you have somebody else finding that error. The cross-check inside these experiments is tremendous.
I guess I'm thinking more along the lines of the double slit experiment.
Of the?
The double slit experiment.
Oh, a double slit experiment. How should I connect this with? Or the answer is no.
Yeah, then the answer is no.
I think the answer is still no. I cannot make
any
connections there. So I think I just answer no. No, I don't think there's any
Thank you very much. Professor Heuer, I know one thing that's not unlimited is energy, both in our lecture as well as in the audience. But Professor Heuer, today from physicists to philosophers, I think we've had a most memorable experience. And with your wit and comfortable way and humor for explaining the essence, I believe, of everything that really matters in all of time, but also in pointing to the future and what exciting routes of inquiry are open to all of us. So would you join me in thanking Professor Heuer for this lecture?